This video is about calculating expected value or payoff values when you have these different games. Okay, so first of all, what is an expected value? So expected value is basically if you were to play a game over and over and over and over and over and over again, would you expect to make money? Would you expect to lose money, right? Would you expect to kind of break even? I think in terms of money, that's the easiest way to think about it. So like a good example would be like if you went to a casino and you were playing like the game roulette, right? If you just stayed there at this table all night and you just kept playing over and over and over and over and over again, how much money would you expect to make or lose per turn on average? So like if you played like 100 times over the night and you ended up walking away losing $100, then you'd say that your expected payout was that you'd lose $1 every time you played, right? So that's kind of the idea of what expected value is. It's not like that every single time you actually lost $1. It's just on average, if you average it out, that's about what you ended up losing. Okay, so that's sort of the idea here. And there's an expected payoff for any kind of game that you play. And that's what we're going to look at with these guys. So this is not a money problem. This is something a little bit different than that, but it still has that same idea of figuring out, like, if you kept doing this over and over, what would you expect the payout to be? So let's look at this one. So this is the game of chicken. You're familiar with chicken, right? Two people are driving their new cars towards each other. If they both continue driving, they crash. If one of them swerves but not the other, the person who swerves loses face from his friends, but the player who didn't swerve is going to like gain rep points, right? So we're going to find the expected payoff for each player. So here's my lovely little table. You'll notice that if they both continue and crash, that is a really bad negative outcome, versus if one of them continues and the other one swerves, it's only a little bit of a benefit or a loss compared to actually crashing your cars and potentially like getting really hurt. Okay, so we're going to start by doing this. There's basically going to be 3 steps here. Step 1 is we're going to find the mixed strategy that each player should follow. Step 2, we're going to use that to figure out how often each of these outcomes will actually occur. And then step 3, we're going to use that to figure out the actual expected payoffs. Okay, so step 1 down here is we are going to find each player's mixed strategy. All right, so we're going to set the expected utility of playing left equal to the expected utility of playing right. I'm going to try to do this all sort of in one step to cut out some space. So I'm going to set the expected utility of left equal to the expected utility of right. Okay, so, oh right, left and right. First off, right, using continue and swerve in this case is not super helpful because we have 2 different continues and 2 different swerves. It's just going to get really confusing if we do that. So by convention, what a lot of times people will do is they'll just say, okay, we're going to use up here and down here, and we're going to use left here and right here, just to make things a little bit more clear as to what we're talking about. Because if I had wrote the expected utility of continue equals expected utility of swerve, you wouldn't have known which player I was talking about. Now that we've kind of changed our vocab, it's very clear what I'm talking about here. All right, so the expected utility of left. So if they play left, every time I choose up, they're going to lose 10. So they're going to lose 10 every time I choose up. And they're going to gain 2 every time I choose down. So they're going to gain 2 every time I choose down, aka 1 minus every time I choose up. Okay. Expected utility of right, every time I choose up, they're going to earn -2. So -2 every time I choose up. And every time I choose down, they're going to get 0. But again, not down, 1 minus up. All right, we'll solve this lovely equation. This is going to cancel out. This is going to give me -10 times the probability of up plus 2 minus 2 times the probability of up equals -2 times the probability of up. Combine some like terms over here. I got -12 times the probability of up plus 2 equals -2 times the probability of up. Add those 12 to both sides, and I'm going to get +10 times the probability of up. And that means that I'm going to get 1/5 for my probability of up. So that tells me that I'm going to have 1/5 of the time they're going to play up, and then 4/5 of the time they're going to play down. Okay, so that's the same thing that we've been doing. So that's step 1. Okay, now for this particular problem, it's actually going to work out to be the exact same if I had done the outcomes for player 2. So you need both players' outcomes, and it's just going to so happen to work out for this one that it's the same for both players. Okay, so if I were to actually do this for both players, right, I would then have to set the expected utility of, up equal to the expected utility of left. And when I go to do that, right, well, every time, so if I choose up, every time they choose to continue, I'm going to get -10. And whenever they choose to go right, to swerve, I'm going to get 2, right? So it would be that same -10 and 2. And then for down, it's going to end up being the same thing. Every time they choose this one, I'm going to get -2. Every time you choose this one, I'm going to get 0, right? It's the exact same numbers that we had here, okay? So when I go to actually look at this one is actually going to work out to be the same. That's not always going to be the case, but for this particular one, it is. So I'm going to fast forward that a little bit. Okay, so that right there is step 1. All right, so now step 2, we're going to come back up to this table and we're going to find the probability of each of these 4 things happening, that either we both continue, one swerves and one doesn't, the other one swerves and the other one doesn't, or they both swerve. Okay, so step 2, here was step 1, here's step 2 up here. Going a little all over the place for this problem, right? So for step 2, right, we're going to find the probability of each outcome occurring. Okay, how am I going to do that? Well, first off, I'm going to take these 4 numbers that we have here and I'm going to label these around this matrix here, or my payoff table. So up is happening 1/5 of the time, so I'm going to put 1/5 here. Down is happening 4/5 of the time. And then over here, that shouldn't have said, what did I even do here? Okay, I'm looking back on this and now I'm like, what did you write? Okay, we were looking at up, this should have said down, right? And then when I solved that, I wouldn't have gotten up and down, I would have gotten left and right, right? So it would have been that my probability of going left was 1/5 and right was here. Okay, there we go, that's fixed. I don't know what happened, I just got lost in my words. Okay, so left was 1/5 and then right was 4/5. There we go. Okay, so to figure out the probability of each of these particular 4 events occurring, all I'm going to do is I'm going to multiply each of these numbers on the outside to fill these cells here. Because if I'm choosing up 1/5 of the time and you're choosing left 1/5 of the time, that means that altogether this is going to come up 1/25 of the time, right? 1 in 5 times I'll do this, but only 1 of 5 times of only one of those 5 times will you be doing this also, and it works out to 1/25, right? This one, if I'm doing this 1/5 of the time and you're doing this 4/5 of the time, that's going to again multiply to 4/25. This one down here, that's going to multiply to 4/25. And this last one here is going to multiply to 16/25. So essentially what this is saying is that if you played this game 25 times, 1 time you would both choose to continue. 4 times I would stay on and you would swerve. 4 times I would swerve and you would stay on. And 16 times we should both choose to swerve. All right, so that was step 2, is figuring those out. So then finally, to figure out what's our expected payoff, is we're going to, for each player, say, okay, well, based on how many times this happened and what my outcome is for each of those times, I'm going to use that to figure out what my expected payout is. Okay, so step 3 over here is I'm now going to find the expected payout. All right, so for the expected payout, so E, and I'm going to use P for this one, the expected payout for player 1, so EP sub 1, the expected payout is going to be that 1/25 of the time they're going to be, this is what's going to happen, and player 1 is going to earn -10. And 4/25 of the time this is going to happen, in which case player 1 earns 2. And 4/25 of the time this is going to happen, in which case player 1 earns -2. And 16/25 of the time this is going to happen, in which case player 1 earns nothing. Okay, and then I'm just going to take all of that and I'm going to multiply and add. I'm going to grab my calculator and do this just so you can see what I'm actually typing in. So I'm doing 1/25 times negative 10 plus 4/25 times 2, oops, 2, plus 4/25 times negative 2. And then the 16/25 I really don't need to, oops, hit the wrong button there. 16/25 I really don't need to multiply by 0 because I know that's just going to go away, but I'm going to do it anyway. So this works out to negative 0.4. All right, and we're going to come back to what that means in just a second. I do want to change this into a fraction though, so hit your math button, top option changes things to fractions. All right, and we want to stick with fractions just because those are a little bit more accurate. So negative 2/5 is our outcome for player 1. So then same thing for expected outcome for player 2, right? So for player 2, 1/25 of the time, player 2 earns negative 10, right? 4/25 of the time, they're going to earn negative 2. 4/25 of the time, they're going to earn positive 2. And then 16/25 of the time, they're going to earn 0. So again, with this one, it just so happens that because these guys have the same payouts and the table is so similar, it's actually going to work out the same, right? These are just turned backwards in this one. This one's also going to be negative 2/5. All right, so what does that mean? It means that by doing this particular activity, playing chicken over and over and over again, right, you are going to expect to have a negative outcome, a loss of 2/5 every time you play on average, okay? So what we're saying here is that each player, that is not how you spell each, my goodness, E-A-C-H, there we go. I got it. Took me like 3 tries, but I spelled that word correctly. So each player, right, is going to expect to lose because it's negative. So they're losing 2/5 every time he plays. Now, this is one where I feel like it makes more sense when you're talking money because then you'd say like, oh, it's 2/5 of a dollar. But in this case, we're not really talking money, right? We assigned these points based off of these like general ideas of whether you're gaining or losing and how much you're gaining or losing. What this basically tells you is that every time that you play chicken, you're expecting to lose in the long run, right? Playing chicken is not a great idea because even though sometimes you might win, in the long run, you're losing overall. On average, you're going to keep losing. Okay, so that's how we calculate an expected utility. So let's look at this one down here. Battle of the sexes. So basically you got this man and this woman who go on a date. The man prefers to see a fight. The woman prefers to go to the ballet. However, they would rather be together than be alone. If the other person doesn't show up, they just go home. So here's our different outcomes, right? If they both end up at the ballet, then player 1, the man, is less happy because he doesn't get to go to the fight that he wants to go to, but at least he's like going out and doing something rather than being home by himself. Player 2 is happy because she got to do the thing she wanted. If player 1 goes to the ballet and player 2 goes to the fight, then they're both unhappy because in that instance, they both just go home and spend the night by themselves. Okay? If player 1 chooses the fight, player 2 chooses the ballet, same deal, they both just go home, right? If they both choose fight, player 2 is more happy because he gets to do the thing he wants. Player 2 is somewhat happy because at least she gets to go hang out with her boyfriend, okay? All right, so we're going to do the exact same thing here. So we're going to find our expected utilities and we're going to calculate this one out. So I'm going to start with, again, saying that these two are going to be up and down, and these two are going to be left and right. And I'm going to set the expected utility of left equal to the expected utility of right. And I'm going to go ahead and build this equation. Okay, so every time you choose to play left, you are going to win 2 whenever I choose to play up. Okay, so whenever he chooses up, she wins 2. And whenever he chooses down, she wins 0, right? So whenever he chooses down, but remember we're going to write 1 minus up, right? And in that case, she wins 0. Okay, if she chooses to go right, then she's going to earn 0 whenever he goes up. So whenever he goes up, she gets 0. And if she chooses right, whenever he goes down, she's going to earn 1. But again, I'm going to write 1 minus up instead of writing down. All right, and then we're going to solve this equation. We got some zeros, so that's pretty nice. Those just go away. So I'm going to have 2 times the expected, or the probability of up. Over here, distributive property, that's just going to be 1 minus the probability of up. So I'm going to add that to both sides. Oops, sorry, I just realized I'm off camera a little bit. I'm going to add this guy to both sides. So I'm going to get 3 times the probability of up equals 1. So that equals 1/3. And therefore the probability of down is 2/3. Right, now this one happens to work out to be another one like the last one we did. Because this game board is so symmetrical, it's actually going to work out to be the same outcomes for playing left versus right. So the probability of playing left is going to work out to be 1/3 and right's going to work out to 2/3. For right now, I'm not going to go through showing that because there's one other thing that I'm trying to point out with this one. So something is going to happen with this that I want to kind of point out to you just to make kind of a case for it. So let's just continue on with looking at this player. So we figured out that player 1, the man, right? He should 1/3 of the time go to the ballet and 2/3 of the time go to this fight. Okay, and this is assuming that they can't talk to each other and plan ahead of time. They're just sort of guessing. Okay, so this was our first step. So now from here, we're going to calculate these. So he's doing this 1/3 of the time and this 2/3 of the time. And again, because this game is symmetrical, right, I can then predict what these ones are going to look like. And it's going to work out that, so just like he should do the thing that he likes 2/3 of the time, she should do the thing that she likes 2/3 of the time. So when I multiply these, this one's going to happen 2/9 of the time. This one's going to happen 1/9 of the time. That'll happen 4/9 of the time. And this one will happen 2/9 of the time. So that's our step 2. Step 2. All right. So now for step 3. And again, I just want to calculate just for one player for right now because I'm trying to prove a point. So for step 3, when we go to calculate the actual payoff, so the expected payoff for player 1, right, is that they're going to get, so 2/9 of the time, they're going to get 1, right? So 2/9 of the time, they're going to get 1, right? 1/9 of the time, they're going to get 0. 4/9 of the time, they're also going to get 0. And then 2/9 of the time, they're going to get 2. Okay, I don't need a calculator for this one. These ones will just go away because they're multiplied by 0. That's just 2/9, and that's going to be 4/9, right? So this is going to work out to 5/9. Oh, no, I'm sorry, 6/9. 2 times 2 is 4, plus 2 is 6. 6/9. I knew I was doing something wrong there, aka 2/3. Okay, so that is the expected outcome. So this is telling me that player 1 expects to earn 2/3, right, every time he plays. Great. Okay, so what was the point that I'm trying to prove? So here's the point that I'm trying to prove. Go back and look at this original game matrix, okay? So when we look at this original game matrix, he's only earning 2/3 every time, right? If instead of doing this whole nonsense of like randomly selecting one each time, right? Look instead at what this possible outcome is. If he had just chosen to go do the thing that his girlfriend liked, right? His outcome would be 1, which is better than the outcome of playing this mixed strategy, right? So what is happening here, right, is that by doing this mixed strategy where you're forced to like blindly guess compared to the other person, right? If you can't coordinate and you just have to blindly guess to try to figure out what happens, then yeah, you have this mixed strategy Nash equilibrium that says you should do this. But like if you can coordinate with the other person at all, you're better off just doing the thing that you don't like as much so you can spend time with your partner, because then your payout is actually better than just blindly forcing your way each time. Okay, so even though we have these strategies, and these are good things that you can use when you are playing against an opponent, once you allow that cooperation facts to come into play, it's going to actually make a difference. It's not something we're going to really focus on in this particular class, but that is something that is like adds a whole new level to game theory.